Hi everyone, this is a video for class 32 of PH 125, and today we're going to be talking about heat and heat transfer, and then we're going to start talking about ideal gases. Okay, so far in our chapter on temperature, we started off by talking about different temperature scales that you might see in this class. So that includes Celsius, Fahrenheit, and Kelvin. We also learned about ways that we can convert between those different temperature scales, which are shown in the red boxes here. Alright, most often in this class we will be dealing with temperatures measured in Kelvin. If you're not sure if your temperature should be in Kelvin or not, it's a good idea to look at the units in the equation that you're using. Most often you are going to want to just go ahead and convert to Kelvin if you're not sure. The exception would be if you have something that has a change in temperature and you require units of Kelvin, because remember, a change in temperature in degrees Celsius is the same as a change in temperature in degrees Kelvin, and so then you can get away with not doing the conversion. But if you're not sure, it's a good idea to just go ahead and convert into Kelvin. Okay, then we talked about this idea of what is temperature, and remember, it's hard to define, but we say that objects in thermal equilibrium are at the same temperature. And so then we might want to know, what is thermal equilibrium? Well, remember, thermal equilibrium is related to heat, and heat is the energy transferred between objects at different temperatures. So specifically, heat is a form of spontaneous energy transfer, and that spontaneous transfer of energy no longer occurs when objects are at the same temperature, and that's when we say that the objects are in thermal equilibrium. In the last class, we learned that when objects are heated, so when their temperature increases, they tend to expand. And in this class, we'll be talking more about heat transfer. Specifically, we're going to answer the questions of how much heat is required to change the temperature of an object, and also how is heat transferred between objects. Okay, so let's go ahead and talk a little bit more about heat. So heat is really just energy transfer between objects due to a temperature difference. And so then you can see that heat really is just a form of energy. Specifically, it's a type of energy that's in transit. So it's always going to be some form of energy that's leaving one system and entering another system. Okay, but because it is just a type of energy here, we then know that the SI units of heat are going to be the same as the SI units of energy, which are joules. Okay, so SI units of heat are joules, but you'll also often see heat measured in calories. So a calorie is what's known as the mechanical equivalent of heat. And really, 1 calorie, where calorie here is a lowercase c calorie, is defined to be the amount of energy that's required to raise the temperature of 1 gram of water by 1 degree Celsius. Okay, so like I mentioned, that's the lowercase c calorie, and it turns out that that's 4.186 joules. All right, then there's also capital C calories. So a capital C calorie is like what's on a food package, and that's actually 1 kilocalorie, or in other words, 10 to the third little c calories. Okay, and so 1 capital C calorie then is 4,186 joules. All right, so you might also see calories when we're dealing with heat. Then if we want to know in general how much heat is required to change the temperature of an object, we define the specific heat of that particular object. Okay, and so specific heat, it's given the symbol little c, and specific heat is defined to be equal to Q, which is the heat added or removed from an object, divided by M, the mass of the object, and delta T, which is the resulting change in temperature of the object. Okay, and so then looking at this equation, C is equal to Q divided by M delta T. Q, remember, has units of joules, M is kilograms, and delta T is going to be in Kelvin. And so then you'll often see the SI units of C in terms of joules per kilogram per Kelvin. Okay. And then this C, this specific heat, is really a characteristic property of the particular material that you're interested in. And so this is the type of thing that you'll be looking up like in a chart, or it might be something that you're given, or maybe it's the thing that you're trying to determine. But it's really a characteristic property of a particular type of material. Okay, and so then we could take this equation for C, the specific heat, and we can rearrange it to determine how much heat is required to raise the temperature of an object by some particular amount delta T once we know the specific heat of that object. And so then what we find is that Q is equal to M, the mass of your object, multiplied by C, its specific heat, times delta T, which is the change in temperature of your object. Okay, and then looking at this equation, you can see that if delta T is positive, so in other words, if the temperature of your object is increasing, then Q is going to be positive as well. And so in that case, then we would have heat entering the system. And so whenever heat enters the system, Q is going to be a positive value. All right, similarly then, if we have the case where delta T is negative, in other words, the temperature of your object is decreasing, then you're going to see here that Q will be negative, and this would correspond to the case where heat is leaving the system. So if heat leaves the system, Q is negative. If it enters the system, Q is positive. Okay, and then oftentimes when we're thinking about specific heat and how much heat is required to change the temperature of an object, or we might be thinking about what is the temperature change of an object due to a certain amount of heat flowing into or out of that object, then we're oftentimes going to be interested in thinking about conservation of energy, because usually you'll have objects that are interacting with each other, exchanging energy as heat, and then those exchanges of energy as heat have to result in conservation of energy. And so in general, the sum of the heat exchanges within a system has to be equal to the amount of heat that's added to or leaves the system. Okay, then if you have this key word that the system is insulated, what that means is that no heat can leave the system or come into the system. And so then the right-hand side of this equation, which I'm calling Q external, which is the amount of heat that enters or leaves the system, that's going to have to be equal to 0 if you have a system that's insulated. And so then the sum of the heat exchanges of the objects within that system will have to be equal to 0. Okay, let's just talk a little bit more about specific heat. So I'll just give you a little warning to be careful with units here. A lot of the times you're going to be given specific heat in terms of joules per kilogram per Kelvin, like the table that's shown on the right-hand side here. But sometimes you might be given specific heat in terms of joules per gram per Kelvin, in which case you would want your mass to be in grams. Okay, then the other thing here is thinking about this temperature. Specific heat is in terms of joules per kilogram per Kelvin. And so then when we think about this specific heat relationship, it's related to change in temperature. So remember, it's okay to keep your change in temperature in terms of degrees Celsius, because a change in temperature in degrees Celsius is the same as a change in temperature in Kelvin, but you will not want to keep your temperature in terms of Fahrenheit. Okay, and if you're not sure what to do, converting to Kelvin is always a good choice. All right, I'll also mention here that if there is an object that has a really high specific heat, that means, looking at our definition here, that a lot of heat has to be transferred to the object to get some change in temperature of the object. And so then looking at the chart on the right-hand side, you'll notice over here that the specific heat of water is actually really high. So you can see it's much higher than many of the other things listed here. And so that means that it requires quite a lot of heat to raise the temperature of water. Okay, and then something else you'll probably hear when talking about the amount of heat required to change the temperature of an object is something called heat capacity. Heat capacity, which is given the symbol capital C, is defined to be the total amount of heat required to change the temperature of an object that has mass m. And so looking at the definition, C is equal to Q over delta T, you can see that really capital C, heat capacity, is just equal to the specific heat multiplied by the mass of your object. Okay, so this is something else that you will hear about in terms of thinking about the amount of heat required to change the temperature of an object, but in general it's going to be less useful because it does depend on the mass of the object that you're heating or cooling. Okay, and so now let's go ahead and talk about how heat is actually exchanged between objects. So here let's think about 3 situations. We want to consider the difference between turning on the seat heater in your car, turning on the heat in your car, and feeling the warmth of the sun through your car's windows. And so all 3 of these are examples of heat exchange, but the methods of heat exchange are different. Okay, and so these exemplify the 3 different methods of heat exchange that we'll be focusing on: conduction, convection, and radiation. So conduction is really heat exchange through a material itself. So this usually occurs when you have objects that are exchanging heat by touching. Convection is heat exchange due to the motion of an unevenly heated fluid, and radiation is heat exchange due to electromagnetic radiation. Okay, and so then thinking about those 3 definitions, what do you think turning on the seat heater in your car is an example of? Okay, so when I turn on the seat heater in my car, then the seat gets warm, and because I'm touching the seat, I get warm too. And so I would say that that's probably a form of heat exchange through conduction because I'm actually touching the seat in my car. All right, what do you think about turning on the heat in your car? Okay, so when you turn on the heat in the car, then a certain amount of the air gets warmed up by the car's heater and it circulates around with the colder air that's also in the car. And so that seems to me like convection, heat exchange due to bulk motion of unevenly heated fluid. So I would say that that's an example of convection. All right, last one here, feeling the warmth of the sun through your car's windows. What do you think about that one? Okay, so the light given off by the sun is really a form of electromagnetic radiation, and so then feeling the warmth of the sun through your car's windows is going to be an example of heating through radiation. All right, let's go ahead and talk about each of these three different forms of heat exchange in detail, starting with conduction. So conduction, remember, is heat transfer through material, and here we specifically want to know how much heat is transferred through a particular material when that material is separating two regions of space, one at temperature T1 and the other one at temperature T2. Okay, so it turns out that the amount of heat that gets transferred through this material via conduction is going to be related to the difference in temperature between those two regions that it separates. It's also related to the cross-sectional area of the material that separates those two regions of space. So in other words, that cross-sectional area is like the area that's going to be in contact with region 1 on one side and in region 2 on the other side of the material. It's also going to be related to L, which is the length separating those two regions of space. So in other words, what is the distance through the material that the heat has to transfer to get from region 1 to region 2? That's that length of the object L. And then it's also related to a material property called K, the thermal conductivity. All right, and so then it turns out that the amount of heat that gets conducted from region 1, which is at temperature T1, to region 2, which is at temperature T2, in an amount of time T, is equal to K, the thermal conductivity, times that cross-sectional area of your object, multiplied by delta T, the difference in temperature between the two regions that are connected by the object, divided by L, which is the length of the object, multiplied by T, the amount of time over which that heat is transferred. All right, let's talk a little bit more about the thermal conductivity K. So K is really just a property of a substance that tells us about how easily the heat is conducted through that substance. It's a characteristic property of a particular material. So just like specific heat, which we talked about a little bit earlier, it's going to be the type of thing that you'll look up in a table. These are well-known quantities that have been measured for various materials, or it might be the thing that you're looking for in a problem. All right, looking at our equations here up above in the blue box, we can see that Q is equal to K times A delta T times time divided by the length of the object. And so if you do a unit comparison and you want to make sure that the units on the left-hand side of this equation, joules, are equal to the units on the right-hand side of this equation, we can see that the units of K have to be equal to watts, which remember are a joule per second, divided by meters divided by Kelvin. Okay, so those are going to be the SI units for the thermal conductivity K, and you can see that those are the units that are given in our table on the right-hand side. All right, let's think a little bit more about this thermal conductivity. So what does it tell us? So looking at the equation for Q given in the blue box here, you can see that if an object has a high thermal conductivity, it can transfer a lot of heat through conduction. Okay, and so then we say that those objects that have these high thermal conductivities, we say they're good conductors of heat. And so you can look at this table on the right-hand side here and see that some things that have high values of thermal conductivity, so in other words, some things that are good conductors of heat, are silver, copper, and gold, for example. All right, what if you instead have an object that has a low thermal conductivity? Well, again, thinking about our equation for conduction here, you can see that if K is low, then it's not very good at transferring heat through conduction. So in other words, that means that it's a good insulator. So it won't transfer a lot of heat over a long period of time. All right, so things that are good insulators are things that you would be interested in having, for example, insulating your home to prevent heat from flowing out of the home when it's cold outside or into your home when it's hot outside. So looking at our table over here, I would look for things that have low thermal conductivities. So some things that you might have heard of, asbestos has a low thermal conductivity, which was why it was used as an insulator in older homes. Now it's known to be toxic, but that's why it was originally used. But air is also quite a good insulator. That's why there's usually air between panes of glass to keep a nice layer of insulating air to prevent a lot of heat from flowing through your glass windows. All right, let's go ahead and do a quick practice problem here. So given your experience of what feels colder when you walk on it, which of the following surfaces do you think will have the highest thermal conductivity? Okay, so to think about this question, I would think back to what the thermal conductivity tells us. So remember, things with large thermal conductivities are good conductors, things with small thermal conductivities are good insulators. And so when you think about you walking on the floor, you are generally at a little bit higher temperature than the floor. The floor would be at room temperature, so your body temperature is usually a little bit higher. And so what that means is that the floor is going to draw heat away from you. All right, and so then when you think about the thing that has the highest thermal conductivity, that's going to be the thing that conducts heat away from you best. And so when you think about how that feels, it's going to feel cold to the touch because it's drawing heat away from you the best. Okay, and so then I would think about the fact here that when I walk on carpet, tile, and wood, the tile feels the coldest. And so then I would say that the tile is going to be the best conductor. In other words, it has the largest thermal conductivity. So I would go ahead and pick answer B here. It's the tile. Okay, so now let's go ahead and talk a little bit about convection, which remember is heat exchange due to the bulk motion of an unevenly heated fluid. All right, so let's just think about a specific example here, which is water boiling on the stove. So here you have water boiling on the stove. The bottom of the pot of water is in contact with the flames, and the flames are going to heat up then the bottom of the water. Okay, so the bottom layer of water gets warmed up due to the flames of the stove, and then we know from our last lecture that things tend to expand when they get heated up. So that water that's at the bottom of the pot, it's going to tend to expand because it gets heated up, and then as it expands, its density decreases. Well, then remember from our chapter on fluids that things that are less dense tend to rise and things that are more dense tend to sink. And so what that means is that the warmer fluid that got warmed up by the flames at the bottom of the pot, it became less dense, it's going to raise to the surface, and then the colder liquid is going to fall down towards the bottom of the pot. Okay, so the warmer fluid rises, the cooler fluid gets pushed down, and then that cooler fluid is in contact with the flames. And so that means that that cooler fluid is going to get warmed up, and then the cycle will continue, and this results in a fluid circulation and heating of the water in the pot. So the boiling pot of water is really just one of many examples of convection, and we'll talk about a few more here. So you may have noticed if you've ever lived near a large body of water, the temperatures near the shore tend to be more mild than temperatures further inland. And so this really comes from the fact that water, remember, has a really high specific heat. And so that means it takes a lot of heat to change the temperature of the water. So the temperature of the water changes more slowly than the temperature on land. Okay, and so then what that means is when it's really warm on land, it tends to be cooler over the water. And so you get this circulation of warm and cold air from the shore and out over the water that keeps the shore a little bit cooler. Then if you have this situation that the shore is colder, well, the water tends to stay a little bit warmer. And so then what happens is you get the circulation of air, the warm air coming off of the body of water and the cool air from the shore so that it keeps the shore a little bit warmer. So that's why the temperatures tend to be a little bit more mild if you live near a large body of water. Okay, so some other examples of convection. Radiation heaters use convection to heat your home. A convection cooker uses convection to cook food more quickly than a regular oven. And also convection is related to how a hot air balloon works. So lots of examples of convection. So now let's talk about our last form of heat transfer, which is radiation. Radiation, remember, is heat exchange due to electromagnetic radiation. All right, so it turns out that we know how quickly heat is radiated from a body at temperature T when that body has a surface area A. So it turns out that the amount of heat that's radiated in an amount of time t, which we could call power, because remember, power is energy per time, and heat is a form of energy. So we refer to this as the power, or in other words, it's the rate at which the heat is radiated. It turns out it's equal to E, which is the emissivity of the object, multiplied by sigma, which is the Stefan-Boltzmann constant, multiplied by A, the surface area of the object, times T to the fourth, where T is temperature measured in Kelvin. All right, so the Stefan-Boltzmann constant, sigma, it's equal to 5.6 times 10 to the minus 8. It has units of watts per meter squared per Kelvin to the fourth. And then the emissivity can take any value between 0 and 1, and it tells you about how effectively an object emits or absorbs heat. Okay, and so something that's really shiny, something that's not going to absorb heat well, it's not going to emit heat well. So something like a mirror is going to have a low emissivity, something close to 0, whereas something that's very dark colored, something which we call a black body, is going to have a very high emissivity close to 1. Okay, and so then this equation tells us about the rate at which heat is radiated from a body, but then that body is often going to be in some surroundings that are at temperature Ts. And so sometimes we want to know what is the net power radiated by the body when it's in some surroundings at temperature Ts, rather than the total power that's emitted by the body. Okay, and so then in that case, we can measure the net power radiated by the body as the emissivity times the Stefan-Boltzmann constant times the surface area of the object, multiplied by the temperature of the object raised to the fourth power, minus the temperature of the surroundings, Ts, also raised to the fourth power. All right, and then I'll just remind you that it's very important in these equations to convert into Kelvin. You'll notice the units of the Stefan-Boltzmann constant are in terms of Kelvin to the fourth, which means that our temperature also needs to be in Kelvin. This is not a change in temperature. I know there's a difference here, but it's temperature to the fourth, so it's not going to be the same thing. So you do have to convert to Kelvin when using these two equations. All right, and that wraps us up for this chapter, chapter 16. Next up, we're going to be doing chapter 17, in which we're going to be discussing phases and phase changes, but we're actually going to start by talking about an ideal gas. Okay, so an ideal gas is really just a simplified model of a real gas, and the ideal gas model specifically ignores interactions between molecules. So we consider the case that the molecules in an ideal gas are not interacting with each other. All right, this is generally a good approximation, especially when we have dilute gases. So in other words, when we don't have gases at very high temperatures and they're not at very high pressures or very high densities. Okay, then it's usually a very good approximation for real gases. All right, so specifically when we talk about ideal gases, we're going to be looking for something called an equation of state. So an equation of state is really just a relationship between the thermal properties of a substance. And so here specifically, we're going to be looking for a relationship between various thermal properties related to an ideal gas. So the thermal properties that we're going to be interested in are pressure, which remember is force per unit area and has SI units of pascals, volume, which is measured in meters cubed in SI units, temperature, which must be measured in Kelvin. So remember here, again, you're going to want to think about converting into Kelvin when we're talking about using ideal gas relationships. And then also number of molecules in your system or number of moles. So here we use capital N for the number of molecules in a system, and we use a lowercase n when we're talking about the number of moles in a system. Remember that one mole contains Avogadro's number of molecules. In other words, it contains 6.022 times 10 to the 23rd molecules. Okay, and so then the number of molecules in a system and the number of moles in a system are related. Specifically, if you have little n number of moles in a system, then the number of molecules is just going to be equal to the number of moles multiplied by Avogadro's number. All right. So in dealing with ideal gases, we're often going to be using the periodic table and getting information from the periodic table. So I'll just remind you of how to do that before we kind of dive into our equation of state here. So here I've drawn out a specific element, oxygen. I've drawn out its square from the periodic table, and I'll just draw your attention here to this number 15.999 that's under the oxygen symbol. Okay, so that number represents the molar mass of oxygen. It tells us that there are 15.999, or in other words, approximately 16 grams of oxygen in 1 mole of oxygen. Okay, another way to think about this by remembering that there are 6.022 times 10 to the 23rd atoms is that 16 grams of oxygen will contain 6.022 times 10 to the 23rd atoms, in other words, 1 mole of oxygen. All right, so that's going to be the molar mass, that's 16 grams. Remember, SI units, we'll probably want to think about kilograms. And then if you need to know the mass per atom, you can just divide that molar mass by the number of atoms in 1 mole. In other words, you can just divide by Avogadro's number. All right, let's just do a little bit of practice here. So which contains the most molecules, 1 mole of water, 1 mole of oxygen gas, or do they contain the same number of molecules? Okay, so here remember that 1 mole always contains Avogadro's number of molecules, and so that means that 1 mole of water and 1 mole of oxygen gas are both going to contain 6.022 times 10 to the 23rd molecules. In other words, they're both going to contain the same number of molecules. All right, now we want to know which one contains the most atoms, 1 mole of water or 1 mole of oxygen gas. Okay, so for this, we want to think about the fact that 1 molecule of water contains 2 hydrogen atoms and 1 oxygen atom. So in other words, 1 molecule has 3 atoms. When we think about oxygen gas, it's O2. So this is what's referred to as a diatomic molecule. It has 2 atoms in 1 molecule. And so then we can see that there are 2 atoms in 1 molecule of oxygen gas compared to the 3 atoms per molecule in water. And so then since they have the same number of molecules, if the water has more atoms per molecule, it's going to have more atoms total. So I would pick answer 1 here, 1 mole of water. All right, last one, which one weighs the most? 1 mole of water, 1 mole of oxygen gas, or is it the same? Okay, so for this, I would use the 2 squares from the periodic table shown up in the top right-hand corner. Here, the molar mass of hydrogen is 1 gram. The molar mass of oxygen is approximately 16 grams. And so then when we think about the molar mass of water, it's going to be 2 times the molar mass of hydrogen. So in other words, that's 2 grams plus the molar mass of oxygen, which is going to be 16. So that's a total of 18 grams per mole. Then when we think about 1 mole of oxygen gas, it's going to be 2 times the molar mass of oxygen. In other words, 2 times 16 or 32 grams per mole. All right, so then I would pick answer 2 here. The oxygen gas has a higher molar mass. And so that means it's going to weigh the most as well. All right. Now let's get back to our equation of state for our ideal gas. So the equation of state came from a collection of other laws that studied the different thermal properties of ideal gases. So starting with Boyle's law, which tells us that if we have a constant number of molecules in a system, or in other words, we have a constant number of moles in our system, and we also have a constant temperature system, then it turns out that the pressure and the volume are inversely related to each other. So in other words, what that means is that the pressure is equal to some constant divided by the volume. Okay, and so here I have a plot of pressure versus volume for various ideal gases at constant temperatures. So the purple line corresponds to a constant temperature of 100 Kelvin, the blue corresponds to a constant temperature of 200 Kelvin, and the green corresponds to a constant temperature of 300 Kelvin. And so then since each of these lines corresponds to a constant temperature, we call each of them isotherms. Iso means the same and therm refers to the fact that they have constant temperature. So every point along each of the lines of the same color is at the same temperature. All right, and so then another way to think about this relationship between pressure and volume, since the pressure is equal to a constant divided by the volume, if you were to think about different points along the same color curve, then the pressure times the volume at some point has to be equal to the pressure times the volume at another point along that curve. So we could rewrite that as thinking about 2 states, some initial state and some final state. We could write that as P initial times V initial has to be equal to P final times V final in the case that both N and T are constant. All right, then there was another law called Charles' law, and Charles' law tells us that if you have a constant number of particles, or in other words, a constant number of moles in your system, and you also have a system at constant pressure, then it turns out that the volume and the temperature are directly proportional to each other. And so what that means is that volume is equal to some constant multiplied by the temperature. All right, so then down below, I have some various plots of volume versus temperature for constant number of particles and constant pressure. These plots are referred to as isobars. Again, iso refers to the same and bar refers to the pressure. So each of these plots that are at the same color refer to plots at the same pressure. So here you can see the yellow plot is at 150 kilopascals, the orange is at 100 kilopascals, and then the red is at 50 kilopascals. All right, and so you can see that these plots, they're just like straight lines. So we have this direct proportionality between V and T. Once again, if you were to be on some particular line here, so at constant pressure, and you were to pick some initial point and some final point, then what you would end up with is that V initial divided by T initial has to be equal to V final divided by T final, since V is equal to some constant times T. Okay, and one last thing to note here is that as scientists were doing these experiments thinking about volume versus temperature at constant pressure, what they noticed is that if they extrapolated back to some temperature of 0 Kelvin, all of the ideal gases, no matter what ideal gas they were working with, would go through a point of 0 volume at 0 Kelvin. And this was actually how the Kelvin scale was defined. All right, so let's go ahead and put these results together. When we do that, we get the ideal gas law, which is the pressure equation of state for an ideal gas. We have two useful forms here. The first is PV is equal to little n times RT, where remember little n is the number of moles in your system, and R then is the universal gas constant or the ideal gas law constant, and R is equal to 8.31 joules per mole per Kelvin. All right, then the second form is the form that we'll be using more often in this class. PV is equal to NKT, where it's capital N. Remember, capital N is the number of molecules, and then K is what's referred to as the Boltzmann constant. So K is equal to 1.38 times 10 to the minus 23rd joules per Kelvin. All right. And then just one last special note here, I'll mention that the left-hand side of this equation, P times V, has SI units of pascals times meters cubed, right? A pascal is for pressure and meters cubed for volume. A pascal, remember, is a Newton per meter squared. And so then the left-hand side has units of newtons times meters, which remember is a joule, in other words, a unit of energy. And so then the left-hand side and the right-hand side have to have the same units, and so that means the right-hand side must have units of energy as well. And so then you can see that K, that Boltzmann constant, it's really like a conversion between temperature and energy, which you can see from its units of joules per Kelvin. So just a little interesting thing to keep in mind. We'll be talking a little bit more about that later on today and in some future lectures. All right, let's do a quick practice problem. We have a piston that creates a volume of 20 milliliters and a pressure of 30 psi for a particular ideal gas, and then you somehow decrease the volume inside that piston to 10 milliliters, and we want to know what is the new pressure. Here we're going to assume that the temperature remains constant, and I'll also mention that we can assume that this piston is sealed so that no gas can escape. Okay, so to answer this one, I would be thinking about the fact that PV is equal to NKT, or PV is equal to little n times RT, whichever you prefer is okay in this case. And we know that temperature is constant, and I said that the piston is sealed, which means that the number of molecules or the number of moles of gas inside the volume is going to be constant as well. And so in other words, what we really end up with here is PV is equal to a constant. Okay, and so then you can just define two states, and you know that P1 V1 is going to be equal to P2 V2. P2 is really the thing we're looking for here. That's the pressure in state 2, which has a volume of 10 milliliters. And so we can rearrange. We end up with P2 is equal to P1 V1 divided by V2. All right, in this case, you actually don't have to convert into SI units here, because if you were to convert between milliliters and meters cubed, you would end up with the same multiplying factor in the numerator and denominator. Same would be true when converting between pressures. You would have the same conversion factor for the pressure on the left-hand side as for the pressure on the right-hand side, and so those conversion factors all just cancel out. And so what that means here is you can just leave things in terms of milliliters and psi, and you should find that P2 is equal to 60 psi, or in other words, answer A here. All right, I will mention that in doing these types of comparisons, you do have to be careful about converting temperature. temperatures don't convert by just multiplying by some factor, right? You have to actually shift the temperature scales. And so whenever you have temperatures, you will need to convert. But if you have quantities that just are multiplicative factors, then you might not have to convert when you're just comparing two states of the same ideal gas. All right. Our last topic for today is something called the kinetic theory of a gas, which really tells us about the relationship between energy and temperature for a monatomic ideal gas. All right, so a monatomic ideal gas is an ideal gas that just has one single atom per molecule. So as opposed to a diatomic ideal gas, which we talked about earlier, which had 2 atoms per molecule, something like oxygen gas. So some examples of monatomic ideal gases, things like helium and neon, those are both single atom per molecule gases. So those are good examples of monatomic ideal gases. All right, so when we first started talking about temperature, we mentioned that temperature is related to the energy per molecule in a substance. So what we're going to do here is we're going to derive that relationship for a monatomic ideal gas. All right, so we're going to start by thinking about pressure. And so pressure in an ideal gas is really going to be due to elastic collisions between the molecules in the gas and the sides of the container that the gas is in. All right, so these are elastic collisions, which is going to be important for us. And we can think about pressure then in terms of force per unit area due to those collisions of the ideal gas molecules with the wall. All right, so for this example, we're going to think specifically about collisions with this right-hand wall here, which has a surface area A. And then when we think about the pressure, it's really going to be due to the force exerted by the molecules as they collide with that wall in the direction that's perpendicular to the wall. All right, so then if we look at this little coordinate system that I've drawn in here, I've defined the direction perpendicular to that wall to be the x direction. All right, so we're going to be interested in the force exerted by molecules as they collide with that right wall in the direction that's perpendicular to the wall, in other words, in the x direction. All right, so that means that we're going to need the magnitude of that force. So how do I get the magnitude of that force? Well, we're going to start with this simple case where we have this box and it just has one single monatomic ideal gas molecule. All right, then that force is really going to be equal to the change in momentum of that molecule as it collides with the wall, divided by the amount of time it takes per collision. So that's what that force is going to be equal to. And this really comes from Newton's second law. All right, so let's think about the magnitude of the change in momentum of the molecule as it collides elastically with this right-hand wall. So imagine it's coming in with some initial velocity, it has some mass m, and so its initial momentum is going to be equal to m times its velocity. And then it bounces off the wall, it's an elastic collision, and momentum is conserved. And so that means when it bounces off this wall, it's going to have a final momentum that has the same magnitude as before the collision, but in the opposite direction. And so then what that means is that the change in momentum from before the collision to after the collision is just going to be equal to the final momentum minus the initial, which is going to be 2 times the initial momentum, or in other words, 2 times the mass of the molecule multiplied by its speed. Specifically here, we're interested in the change in momentum in the x direction, so this is going to be the speed of the molecule in the x direction. All right, so that's going to be my change in momentum of this molecule as it collides with the wall in the x direction. Then we also need to know delta T to come up with this force exerted by the molecule as it collides with the wall. All right, so what is delta T? I already mentioned that delta T is really the time between collisions with that right-hand wall. So another way to think about that is the amount of time it takes the molecule to travel from that right-hand wall over to the left-hand wall, which it will collide with as well, and then back to the right-hand wall. All right, and so how long does that take? Well, that's going to be related to the distance traveled, which here when you think about going from the right-hand wall over to the left-hand wall and then back again, that's 2 times the length of this container. So in other words, the distance traveled is 2L. It's also then related to the speed of the molecule in the x direction. All right, and so specifically the speed of the molecule in the x direction is going to be equal to 2 times the length of the container, which remember is going to be equal to the distance traveled by the molecule divided by the amount of time it takes to travel that distance. So then we can use that to find delta T by just rearranging this equation. So delta T is just going to be equal to the distance traveled by the molecule, 2L, divided by its speed in the x direction, Vx. All right, so now we can put this together to come up with Fx, the force exerted by the molecule as it collides with the right-hand side wall. Then we end up with 2mvx from our change in momentum divided by 2L divided by Vx. Rearranging a little bit here, we end up with mvx squared divided by L. All right, then what we can do is we can go ahead and divide by the area of the right-hand side wall to get the pressure at the right wall. Then we can see here that we have in the denominator A times L. A is going to be the area of one side of the box. L, remember, is the length of the box. And so then I would say that the total volume of the box is going to be A times L. So we can rewrite this pressure as mvx squared divided by the total volume of the box. Okay, and so now we know what the pressure would be if we just had one molecule with mass m and speed in the x direction of vx in this box of volume v. But really, we're most often going to want to have more than one molecule in the box, right? When we're thinking about a system, most often that will be the case. And so now we want to generalize this expression for a single molecule to the case where we have n molecules. So in that case, we can think about the total pressure as just n times the average value of the pressure per molecule. So the average pressure per molecule is really just going to be like the pressure that we had for a single molecule, where I've replaced Vx squared with the average value of Vx squared. So in other words, this is going to be the average value of the x component of the speed of all of the molecules in the box squared. All right, and then we have this term here, m times Vx squared average. That's looking a little bit like kinetic energy to me, and so that tells me that we're going to be able to relate the pressure to the average kinetic energy of the molecules in this box. So how do we do that? Well, really the average kinetic energy is going to be 1/2 m, the mass per atom in the box, multiplied by the average value of the speed of each atom squared. Okay, and so then this speed squared, that's really going to be related to the velocity of the atoms. It's the magnitude of the velocity of the atoms. And so these atoms, they're bouncing around in 3D. And so that velocity is going to have x, y, and z components. And so then using a generalization of the Pythagorean theorem into 3 dimensions, we can say that v squared is going to be equal to vx squared plus vy squared plus vz squared. All right, and so then the average value of the speed squared is equal to the average value of the x component of the speed squared plus the average value of the y component of the speed squared plus the average value of the z component of the speed squared. All right, then our last step here for relating to the pressure equation up above is to recognize that there really isn't any reason why the molecules would be traveling faster in the y direction than the z direction, or the z direction than the x direction. Really, they're all going to be traveling in about the same speed in all 3 directions. So there's no reason that that wouldn't be the case. And so then we can say that the average value of the speed squared is approximately equal to 3 times the average value of the x component of the speed squared. All right, now we're ready to relate to the pressure, because what we can do is we can go ahead and replace v squared average with 3 times vx squared average, and then we can relate to the pressure, and what we find is that the pressure is going to be equal to 2/3 times the number of molecules in the box divided by the volume of the box times K average. All right, and then our last step, remember, in our goal of relating the kinetic energy to the temperature of the ideal gas, is to remember the ideal gas law, PV is equal to nKT. Then what we can do is we can replace N divided by V with P divided by KT. Our P's end up canceling, and we're left with K average is equal to 3/2 KT. And so now we have a relationship between the average kinetic energy per particle in our ideal gas and the temperature of the ideal gas. All right, we're going to leave it there for today. I will see you guys in class.